Welcome to In 5 Minutes. In this video clip, we will discuss the second type of pulse modulation technique, which is called pulse width modulation. Now, as the name suggests, in this particular modulation technique, we are going to vary the width of the pulses in proportion to the modulating signal. In case of PAM, we used to vary the amplitude of the pulses, whereas now we will vary width of each and every pulse. So we still have the same carrier sampling pulses. The carrier signal is still in the form of pulses, where width of every pulse will be a constant value, which can be assumed to be, let's say, tau. And you can see the time gap between the two pulses is Ts. Ts will be nothing but the sampling time period. We use this notation sampling time period and 1 by Ts sampling frequency because it is as good as similar to the sampling process where we sample the original analog signal and keep its values only at some discrete time instance. We are doing something similar in pulse modulation also. Every pulse will only occur at specific time instant and it will read the information from the modulating signal. And after that, before the second pulse arrives, the output signal will be 0. So any pulse modulation is similar to nothing but the sampling, and hence we are using the notation sampling time period and sampling frequencies. But yes, it is PAM which can be defined to be sampling, especially when we talk about natural practical sampling. PWM and PPM, we will use pulses as carrier signal, but because we are not changing the amplitudes, we are changing width in PWM. It is not exactly same as sampling process. Now let us see what is pulse width modulation first with the help of waveforms. You can see this is my modulating signal. Original pulses are of constant amplitude. As the modulating signal increases in its amplitude, the width of the pulse will also increase. You can see when the modulating signal is maximum, the width of the pulse is also maximum in this case. As the modulating signal decreases in its amplitude, you can see the width of each and every pulse will also decrease. When the magnitude of modulating signal is minimum, the pulse width is also minimum, and thereafter as modulating signal increases, pulse width will also increase. So this time, very interestingly, we have put the information in nothing but the width of pulses. So this time the information is in the widths of all the pulses that we have. Unlike the previous case where information was in the amplitude of the pulses. Alright. Let us see how to generate PWM signal and how to demodulate PWM. And then we will see the third type of pulse modulation, and finally we will compare all the three types. Please note that in PWM the amplitude will not change, it will remain constant. So one advantage of PWM over PAM will be that because there are no amplitude variation, the effect of noise will be less. If at any point of time pulse amplitude is different, then it is only due to the noise, and my information will not get disturbed because information is present in the width and not in the amplitude. Whereas in PAM, if the amplitude changes, that cannot be related to the presence of noise only, because those amplitude variations could be due to the change in modulating signal also. In short, because information is in amplitudes, the effect of noise will be more in PAM signal.